numeric data. Now, there is a term that is called a Z score, represented by the Z. That is, Z is nothing but x minus mu divided by sigma. Now, what is mu? Mu is nothing but a mean of the population, and sigma is the standard deviation. Okay, so and what is x? X is nothing but the raw score to be standardized. It is a raw score. Now, what is, if you have numeric data and you want to standardize it by calculating the Z score? Okay, so how to calculate that Z score? That is calculated using the that is whatever the representation is given here. X equals to that is a raw score to be standardized. Mu is equals to mean of the population, and sigma is the standard deviation. So in this way, the Z score is calculated. That is Z equals to x minus mu divided by sigma. Now the distance between the raw score and the population mean in units of the standard deviation. That is, Z score is nothing but it is the distance between the raw score and the population mean in units of the standard deviation. You can see over here that this is x minus mu is with the distance in units of the standard deviation. That is, it is the distance between, this is the raw score, and the population mean is mu. So Z score is nothing but it is the distance between the raw score and the population mean in units of the standard deviation. Okay, so it is negative when the raw score is below the mean, that is plus when above. That means Z score is negative. Z score is negative when the raw score is below the mean. Means if the raw score is minus, if is that is mean is equals to 1, and that x is that little bit lower than the 1, so that the at that time the Z score will be negative. If the Z score is above the mean, then it is positive. Z score is above the that mean, then it is positive. This is what exactly the negative and positive Z score is. That means the raw score should be always above the what? Above the mean. This x should be more rather than the mean. If it is lower than the mean, it will be negative. That means the Z score will be negative. Okay, so this is what exactly the Z score is. Okay, then there is another alternative way to calculate the mean absolute deviation. Okay, so that mean absolute deviation is calculated by using this SF equals to 1 by n mod of x1f minus mf plus mod of x2f minus mf, so and it will be go on, that is up to the xnf minus mf, where what is this mf? This is what is this mf? It is the 1 by n x1f plus x2f up to xnf. So this will be the mean absolute deviation. This will be the mean absolute deviation. Then what is the standardized measures? Standardized measure or Z score. So Z score equals to XIF, that is x minus mf. That is, what is this mean? This is the mean absolute deviation divided by SF. The SF is the mean deviation or standard deviation. So using the mean absolute deviation, it is more robust than using the standard deviation. That means what do you, instead of using the standard deviation, you should use the absolute deviation, so that there will be more accuracy. Okay, we can see over here, we will see one example of this, that data matrix and dissimilarity matrix. We will see one example. You can see over here on x-axis the graph is plotted. This is 2 4, again y-axis 2 4, and the data matrix we will see the points are x1 x2 x3. These are the points. Okay, so what will be the attribute for x1? For the attribute for x1 is 1. Okay, for x2 it is 2. Okay, this is x2. Then x3 2, you can see over here, and x4 is there. The x4 is the 4. This is the value. Again, attribute 2 is there. Attribute 2 is, this is the first attribute. This is the first attribute for x1. Second attribute for x1 is 2. Second attribute for x2 is, this is 5. Second attribute for x3 is 0, because it is 0. You can see over here, this is 0. Okay. Second attribute for x4 is 5. You can see over here, this is 5. So these are the data matrix for the every point. So here 4 points are there: x1, x2, x3, and x4. These are the 4 points. So it has the 2 attribute, attribute 1 and attribute 2. Okay. So we will see the with Euclidean distance. First, we will see the dissimilarity matrix using the Euclidean distance. Now you can see over here x1, x2, x3, x4, x1, x2, x3, x4. Okay. Now you can see the Euclidean distance x1 to x1 0, x1 to x2 there is no distance. Then distance between x2 and x1 is 3.61. Distance between x2 and x1 is 3.61. Distance between x3 and x1 is 5.1. Distance between x4 and x1 is 4.24. Okay. So, distance between x3 and x2 is 5.1. Distance between x4 and that, like that. So this will be the triangular matrix. You can see the triangular matrix. You can see the diagonal elements are 0. Diagonal elements are 0. So this is the triangular matrix. So this matrix will be the dissimilar matrix. Okay. So this matrix is called as a dissimilar by using the Euclidean distance. By using the Euclidean distance formula, we can calculate the Euclidean distance. You can see over here the distance between x1 and x2 is, there is no point. Distance between x1 and x3, there is no point. X1 and x4, there is no point. Then distance between x2 and x3, there is no point. X2 and x4, there is no point. In this way, the distance between x3 and x4, there is no point. But the x4 to x4 is there, 0 is there. Okay. You can see the again the distance between x3 and x3 is 0, x2 and x2 is 0, x1 and x2 is 0. That means the diagonal elements are 0. The diagonal elements are 0. By using the Euclidean distance formula, we will get this dissimilarity matrix. Okay. Again, the distance of numeric on a numeric data, that is, it is also called as Minkowski distance. This is not actually important, but the one formula is there that is used in on the numeric data for calculating the distance. That is called as Minkowski distance formula. The popular distance measure is, for example, that dij, that is distance between I and j, equals to root of xi mod of xi1 minus xj1 plus xi2 minus xj2 plus and so on up to x mod of xip minus xjp. So what is I here? What is I? Whatever is the xi1, xi2, that is what is I? I is nothing but the xi1, xi2 up to xip. It will be the from 1 to p. That value will be from 1 to p. Now what is this p? P is nothing but the dimensions. This is the p-dimensional data objects. P is nothing but it is a p-dimensional data objects. And against what is j here? J will be xj1, xj2, xjp. Okay. So what is p? These are the p-dimensional data object. X and what is x and j? I and j are the x-dimensional or p-dimensional data objects. And what is the h? H is the order. You can see over here, h is represented over here. So h is nothing but the order. That is, it is also called, it is a distance so defined is also called as LH norm also, LH norm. So h is the order. You can see over here, h might maybe 1, 2, 3, 4, 5. H is the order. For example, you can put the value here mod of xi1 minus xj1 raised to 2 or raised to 3 raised to 4. That is, this is the order. Okay. Some properties of this Minkowski distance are that dij is greater than 0 if I not equals to j and dii equals to 0. That is, this is positive. This is positive definiteness. Okay. That means what? The distance between the I and j is greater, always greater than 0 if I not equals to j and dii equals to 0. Again, second property is dij equals to dji. This is symmetric property. Dij equals to dji. Third property is dij less than or equals to dik plus dkj. This is also called as triangular inequality property. Okay. The distance that satisfies this property is a metric. See, in Minkowski distance, these are the three properties. Okay. Now, these three properties should be satisfied by these properties. Okay. Now, we'll see later on this example on Minkowski distance. Again, same graph is there. You can see over here. These are the points. We'll see some example on the Minkowski distance. Okay. You can see over here points are x1, x2, x3, x4. Attributes are 1 and 2. You can see over x1. Consider the point x1. The attribute of x1, attribute 1 for that x1 is 1. Attribute 2 is 2. You can plot here. You can see over here. Attribute of x1. First attribute is 1 and second attribute is 2. If you talk about the x2, this is the x2. The attribute first is 3. This is 3. And attribute second is 5. Okay. Then for the point x3, attribute 1 is 2. This is 2. Okay. Then attribute 2 is 0. Attribute 2 is 0. Then for the point x4, attribute 1 is 4. Okay, this is 4. And then attribute 2 is 5. Okay, so this is what exactly the matrices are there. So we will see the three distances over here, that dissimilarity matrices. You can see over here. By using the Manhattan formula, that is also represented by the L1, you can see over here the distance between x1 and x1 0. Distance between, there is no distance between the point that x1, x2, x3, x4. Then the distance between x2 and x1 is 5. Distance between x2 and x2 0. Then distance between, this same is there, that by using the Manhattan distance formula between these points. Okay. For example, distance between x2, x4 and x1 is 6. Distance between x4 and x2 is 1. Distance between x4 and x3 is 7. Distance between x1, x4 and x4 0. Okay, so this is what by using the Manhattan distance formula. Now we will use the L2, that is called the Euclidean distance formula. By same by using this table only. Okay, point and attributes, by using the attribute 1 and attribute 2 for this, and by using that Euclidean formula, you just put these values in the Euclidean formula, that is x1 and x2. You can see over here it is 0. A distance between x2 and x1 it is 3.61, whereas in Manhattan it is 5 between x2 and x1. Okay, distance between x3 and x1 2.2. Again, that the distance between x1 to x1 0, x2 to x2 0, x3 to x3 0, x4 to x4 0. Okay, you can over here. Again, this is the triangular matrix. Here also triangular matrix. That means this is the dissimilarity of matrices. This is the dissimilarity of matrices. Again, we will see the, by using the spectrum for these points. You can see over here x1, x2, x3, x4. Again, x1, x2, x3, x4. Okay. Distance between x1 to x1 0, x2 to x2 0, x3 to x3 0, x4 to x4 0. But the distance between x2 to x1 is 3, whereas in Euclidean distance x2 to x1 it is 3.61. Distance between x3 to x1 is 2, whereas it is 2.24. Distance between x1 to x4 to x1 3, it is 4.24. Okay, distance between x3 to x2, it is 5, whereas by using the Euclidean distance, it is 5.1. Okay, and then the distance between x4 to x3, it is 5. Okay, whereas in by using the Euclidean formula, it is x4 to x3, it is 5.39. This means what, that there is a difference between the different distance formula, that is Manhattan, Euclidean, and spectrum also. Okay, we will see the ordinal variables. Now the ordinal variables it can be discrete or it can be continuous. Now that what is important in ordinal variable, the order is important. In ordinal variable, the order is important. Okay, that is for order is nothing but the rank. Order means the rank, or it can be treated like a interval scale also. Okay, ordinal variable means variable which has a rank, a variable which has a rank, or ordinal variable can be, it can be discrete or it can be continuous variable. Okay, then what is important here is rank is important now, and it can be treated like interval scale out. For example, you can replace xi by the rank, that is rf belongs to 1 to m. Sorry, so rank may be 1 2 3 up to m. Okay, now then you have to map that range of each variable onto that interval, that is interval between 0 and 1. Whatever the range you got, so you have to map that range of each variable onto the range between 0 1 by replacing the ith object in the fth variable by using the that J score formula, that is ZIF equals to RIF minus 1 divided by MF minus 1. So you have to compute the dissimilarity using methods for the interval scale variables. Okay, so this is what exactly the ordinal variables are there. So ordinal variables are those variables which has the rank. Okay, or it can be continuous or it can be discrete also. Okay, so this was all about today's ordinals variable. Just a minute.